Speaker Raspberry Simpson, Raspberry from Massachusetts Institute of Technology.
Her field is plasma physics, and the advisor is Lindley Winslow. Raspberry's done residencies at Lawrence Livermore National Laboratory in 2019 and 2020. This is an outgoing fellow talk, so congratulations, Raspberry.
Hi, everyone. My name is Raspberry Simpson. I was an LRGF fellow, and it's really a pleasure to be able to be here with all of you in person. And I'm really excited to be able to talk a little bit about my PhD research that was funded and supported by Krell and LRGF. So the title of this talk is Towards Tunable Laser-Driven Particle Sources, New Scaling Relationships, Analysis Tools, and Technology in Laser-Driven Particle Acceleration. So you'll see this cartoon a bunch throughout this talk. I think it really does a good job of illustrating what I mean by laser-driven particle acceleration. So essentially we take kind of this short pulse laser, we're interacting it with this material that I'll talk a little bit more about, and we're able to kind of produce really high energy sources of particles. So over the years, as being part of LRGF, I've had the opportunity to collaborate with a lot of people. So you'll see a lot of them are Livermore folks, since that's where I did most of my residencies. But LRGF has really allowed me to kind of open up my network with folks at academic institutions, both domestically and abroad, being able to travel to international laboratories, for example. So this has really been the key point of Krell and LRGF and SSGF, in that you're able to make these connections with lots of smart people and nice people. So just in true national lab style, I'm putting the summary of my talk up front. So hopefully these bullet points will make a lot more sense at the end of this talk. But if you, basically the subject of this is that ultra intense short pulse lasers, when they interact with matter, we can use them to produce really high energy sources of particles. So charged particles like protons, electrons, positrons, but also neutrons. And we care about these types of sources, I'll talk about, because they can be applied to lots of different interdisciplinary applications. So things like material science and even fusion energy applications. So in this field right now, it's, I think, a really exciting time in the field. I think everyone says that, but I do believe it's really exciting time, and that there's a lot of emerging technology happening. So things like high repetition rate laser systems, where we can fire lasers at hertz or multi-hertz levels, and things like machine learning, and that how are we going to be using all of this data that we're getting from these high rep rate laser systems more effectively. So my PhD research really focuses on these 4 bullet points. One is investigating new empirical relationships for laser-driven proton acceleration. So essentially, how does changing parameters about the laser change something about our resulting particle characteristics? The second bullet point is kind of conducting new measurements around the accelerating electric field responsible for laser-driven proton acceleration, and specifically, so kind of understanding the underlying fundamental physics of this type of mechanism. The third bullet point is demonstration of kind of new analysis methodology using machine learning, so one of these emerging technologies. And then this fourth bullet point is really a proposed methodology that I'm using and developing in my postdoc, actually, that builds on all of this PhD work that I was able to do through Krell. So I'm only going to be focusing on this first bullet point, investigating new empirical relationships for laser-driven proton acceleration. I'm doing that because all the data that is in this first bullet point was actually from my first residency as part of LRGF. So I like to be a big fan of nostalgia, or just reflecting on getting older. So I think that was kind of a nice way to have an outgoing fellow talk that's based on my first ever experience with Krell and LRGF. So just a little bit of background. So I've been talking about lasers and throwing around words like ultra intense lasers. So this is kind of what I mean by that. And that laser intensity has really grown substantially over the last few decades from 1960 when the laser was first invented. So on this, the y-axis, I have laser intensity in watts per centimeter squared. So basically how much power you're able to focus on in a laser spot. And then on the x-axis, I have time. And you see that there's kind of this creep up of intensity over these last couple decades. And kind of the landmark of our field of ultra-intense short pulse lasers, or just high-intensity lasers in general, was this invention of chirp pulse amplification. So this was Donna Strickland actually did this work as a PhD student. She was recently awarded the Nobel Prize with her advisor, Gerard Moreau. But so basically what this invention of CPA allowed us to do, or allowed them to do, is to kind of creep up in laser intensity. And now we're kind of in this plasma era where you have a more intense laser, you're able to ionize your material and create plasmas. And there's a lot of cool applications for kind of being in this era of high intensity lasers. So since their work in the 80s of inventing CPA, there's been a kind of this explosion of petawatt class lasers in demand globally. So here we have these dots here kind of showing where all the location of our petawatt class lasers in the US, also in Europe. You also visited one on Tuesday since you were at NIF, and you're able to see the ARC, the advanced radiographic capability, I think, as well. And I also wanted to point out that my PhD research has been able to kind of span a lot of these facilities as well through the support of Krell and LRGF. So you'll see that some data was taken at NIF Arc, the JLF, which is the Jupiter Laser Facility, which is a smaller laser facility at Livermore. But also my PhD has taken me to Omega EP at the University of Rochester, and then most recently also at the Hopples Laser, which is in the Czech Republic, which was built in collaboration with Livermore. So I'll talk a little bit about each of these facilities and work that I've been able to do at each of them. So you'll see this cartoon again. Shout out to the Livermore illustration team. They really do a good job of turning my PowerPoint cartoons into actually something reasonable. But I also wanted to talk a little bit about the applications that I mentioned previously. So these laser matter interactions enable a lot of interdisciplinary applications that we care about in the program as well, but just in our field of high energy density science. So one of them is actually using laser-driven protons to radiograph material, so we can probe density variations or electric and magnetic fields within a material. We can also do materials at kind of extreme temperatures and pressures, so using laser-driven protons to actually damage a material and then actually probe it using laser-driven particles. You can also do non-destructive evaluation of really dense objects, so in this case using laser-driven neutrons to probe materials. There is medical physics, so using laser-driven protons as cancer therapy, nuclear reactions in plasmas, and then also, interestingly, there are some alternative inertial confinement fusion concepts that use laser-driven protons as kind of a spark to our reaction. So that's something that is gaining a lot more interest again at Livermore, given the kind of recent results that happened in December. But realizing all of these applications really requires a tool where we can predictably relate the parameters of our laser to our output characteristics of our laser-driven protons or laser-driven sources in general. So what a powerful really tool would be to be able to kind of adjust the laser and be able to adjust characteristics of your sources on the fly. So before we get to that, I've been kind of mentioning a little bit about these kind of laser-driven proton sources. So I just wanted to pause to talk a little bit about what exactly that is and how you actually produce a laser-driven proton source in the first place. So there's lots of different mechanisms to do that. The most widely researched is called TNSA, or target normal sheath acceleration. And the kind of the recipe for that is that you take a thin foil, usually 5 to 50 microns thick, typically aluminum or titanium, and you take your petawatt class short pulse laser, which there's kind of many of them now around the world. And what that does is that it creates a plasma. So you have this plasma blow-off region that I'm showing here. And essentially, there's electrons in this plasma region. This laser can actually accelerate electrons via something called the Ponder motive force to really high energies. And those really high energy electrons can actually escape out the rear of this foil. So these are kind of MeV energies. And what that does is that on the surface of this foil is usually kind of hydrocarbon contaminants, things like water droplets, oil droplets. And what that means is that you have this really rich source of ions on the surface of this foil. So by charge separation, you're actually setting up a really strong electric field. And this field is strong enough to actually rip off these ions off the surface of this foil to produce your source of accelerated protons, or ions in this case. And one thing that I wanted to note, to just kind of get to this tunability question a little bit later in the talk, is that if you kind of zoomed into this electric field that is actually responsible for acceleration in general, you'd see nothing. You'd see that there is a lot of structure, and it evolves in time and space. So these are actually 2D simulations of this electric field that is responsible, this sheath field that's responsible for acceleration. And I mention this now because later on in the talk, this is kind of the basis of my postdoc research, is kind of investigating this in more detail to be able to actually tune your electric field to get more tunable proton sources. So going now into kind of the technical research, I like to divide my thesis research into kind of 3 main buckets. So the first are kind of like these building blocks, basically, to get to this larger problem of solving kind of a tunable laser-driven source. The first kind of building block is this brute force empiricism. So I'll talk about basically what I did to gather experimental data on the scaling between these laser-driven sources and laser parameters. I'll talk a little, actually skip over this part, which is this kind of middle building block of dynamic experiments for control. So actually understanding and measuring that electric field that's responsible for acceleration. And then I'll talk a little bit about this kind of emerging technologies that our group is really focused on at Livermore, which are smart laser-driven sources or autonomous laser-driven sources, which are using these high rep rate lasers and machine learning to kind of produce these laser sources on the fly. So now we're kind of getting into the meat of it, where this scaling studies between laser parameters and laser-driven sources, just to kind of give you a sense of the community and the research that's been done. Here, what I'm plotting is the maximum proton energy achieved on these kind of laser-driven proton source experiments versus laser intensity. And one thing to note is that each one of these green points represents a single experiment on one of these petawatt class lasers. And also an interesting and important thing to note is that these were all done with lasers that have a pulse duration below a picosecond. But since the kind of invention of TNSA actually, or the discovery of TNSA since 2000, there has been a large body of work in this field. And given that, there's also been a lot of scaling relationships developed to kind of understand all of these different data points within this sub-picosecond regime. So one of them is this Fuchs scaling for proton energy, which relates the maximum proton energy to actually the T hot, so the temperature of those population of electrons that are actually driving your sheath field in the first place. And this T hot is actually related to the laser intensity that you're using and the wavelength of the laser. So what I'm plotting here is actually the Fuchs scaling for pulse durations from 30 femtoseconds to 700 femtoseconds. And what you're supposed to get away from this slide is that basically the Fuchs scaling does a really great job of representing all of this data in this sub-picosecond regime. But as part of my residency, so this first residency, I was at Livermore. I was working with the team led by Tammy Ma that was doing these experiments on NIF Arc, or NIF, the Advanced Radiographic Capability. It is a short pulse laser that's actually diverting some of the NIF beams to be able to produce a short pulse high intensity laser at NIF. And what they were able to see is that the NIF Arc actually exists in a kind of a strange laser parameter space when you compare it to previous research. So in particular, it exists in that it produces pulse durations much longer than a picosecond. So a picosecond, 10 picosecond, up to 40 picoseconds, which was kind of strange in terms of laser parameter space compared to other facilities. So the kind of central problem back then was that if we extended this Fuchs scaling to 1 picosecond and 10 picosecond, kind of the operating range of this NIF Arc laser, would we still get in kind of maximum proton energies that were useful? So if you look at this curve, so these are the dashed lines of the Fuchs scaling for these different pulse durations. And you can see that we actually did experiments on the NIF Arc laser, and they far exceed what you'd expect just kind of trusting this scaling that was based largely on sub-picosecond data. So there's also a couple other facilities that kind of exist in this multi-picosecond regime, so pulse durations above a picosecond, which I'm plotting in red. So this was kind of you also see that they're existing above this Fuchs scaling. So when I came to Livermore in 2019, this was kind of the central problem in that we had this data from the NIF Arc that wasn't really following the scaling that we kind of expected from all this previous data because the NIF Arc is a strange kind of laser. So my task during that summer was actually to go to the Titan laser facility, which is a smaller laser at Livermore. This is kind of a picture of its target chamber, and do a detailed scaling study of different pulse durations and laser intensities and actually measure the maximum proton energy and try and kind of fill in this gap in data in this multi-picosecond regime. So in terms of diagnostics for that experiment, we had the Titan laser. We were shooting that on a 15 micron thick aluminum target. We're getting this TNSA mechanism, so we're producing protons. We have this radiochromic film stack, which is just film that allows us to get a discrete proton spectrum, basically. And we also had an electron spectrometer to measure electrons that are actually escaping from the target that are kind of responsible for this accelerating field in the first place. This iPhone photo from back then is me in 2019 during my residency. So this is inside the target, the Titan target chamber. You see a picture of the target itself. It's very tiny. This big kind of green block is this proton spectrometer based on film. And then we have these electron spectrometers that we're measuring our electron spectrum. Just to kind of pause on like reflections of my first residency, this was the first time I'd been in a facility like this. I'd never done kind of a mid-scale laser experiment before. So actually being physically in a target chamber, setting up diagnostics was completely new to me. I was definitely very excited, but I was also very nervous because I was like, I don't know what I'm doing, and which was true. And that's okay because you have a team of people as all the national labs, also including Livermore, that are there to help you. For many of you, when you go to residencies, this will be the first time that you're existing with a piece of equipment that is the only one in the world. So it's very normal to just have a learning curve, and that is like to be expected. And I feel like this was maybe one of the scariest professional experiences, but also the most rewarding. And I had a lot of fun that summer. So to any new people kind of looking for residencies, I hope that you can get out of your comfort zone, and that's actually kind of can be a comfortable place after you're done. Right, okay, so this is actually the data that we took that summer. So here I'm showing the measured electron temperature from those spectrometers versus laser intensity. We were scanning multiple different pulse durations from 1 picosecond up to 20 picoseconds. So this is kind of allowing us to kind of fill in this data space that we didn't previously have. What I'm plotting here is this equation that I kind of flashed up a few slides ago, which relates T hot, so this temperature of electrons, to the intensity and wavelength of the laser. This is called the Wilks scaling, and this is this black curve right here. And you can see that for this multi-picosecond data, the thing to to note is that all of these points exist above it. And there's also different scalings that also are kind of based on sub-picosecond data. And again, all of these points kind of exist above them. So this is the maximum proton energy that we measured on that experiment versus laser intensity, again, for our 4 different pulse durations that we are investigating. Here, I'm plotting the Fuchs model. So that model before that did a really great job of explaining sub-picosecond data, but really wasn't explaining our NIF Arc data. So again, you see that these multi-picosecond points kind of don't really follow the Fuchs scaling. And part of that summer was kind of trying to think about how to modify the Fuchs scaling to kind of better capture the data that we saw on Titan, but also on the NIF Arc. So this is kind of this modified Fuchs scaling that I worked on with Dean Rusby. And you can kind of see that for many of the pulse durations, you kind of are getting a better relationship between maximum proton energy and laser intensity. So just to talk a little bit about what's in that, basically what is changing is kind of adjusting this T-hot parameter and also things relating to the kind of this TP parameter that I didn't really talk about, but is related to kind of the acceleration time of the protons using a different formulation by Carey Brenner, and also kind of just ad hoc increasing this T-hot because we had all this data of the electron temperature that was enhanced from this kind of Wilks scaling. So I'm adding my points that we took at Titan to kind of the landscape of data on the sub-picosecond data. Since then, I guess 4 or 5 years ago now, these scaling studies are really important, have been important to being able to use the NIF Arc for laser-driven sources elsewhere. There's also obviously limitations to this in these types of kind of brute force empiricism. And this is kind of leads into what we're working on now in our group. So same group that I did my practicum residencies with, where we're using kind of these smart laser-driven sources or trying to develop them. So I kind of alluded to in the beginning that there are now high rep rate or high repetition rate laser systems. So something like NIF only shoots 1 shot per day, basically. Something like Titan, we get about 6 shots per day. The Hopples Laser, which was built by Livermore in collaboration with Eli Beamlines, so this site was actually in Prague in the Czech Republic, is able to shoot at 10 hertz, so 10 times a second. And that is really just kind of a leap for our field, in that you're able to basically do my residency that took 4 months in maybe a day. So being able to understand how we can start to use these types of facilities and combining them with things like machine learning is really where, at least in our group at Livermore, we kind of see the community going. So this is kind of the Hopples Laser again, and showing that these high repetition rate laser systems really represent a paradigm shift in our field. And it's really interesting to be able to see that and reflect on that from the Titan experiment and during that first residency, and then kind of being able to go to Hopples last year as a postdoc. So this is kind of our vision in our group of what we mean by smart laser-driven sources. So there's a lot happening here, but basically what it means is that you have your laser control system that is operating at hertz repetition rates. You're able to shoot that at a target that is also operating at hertz repetition rates, so kind of replacing that aluminum target that I mentioned before, or maybe a gas target. You are able to also collect data at hertz repetition rates and then also analyze it. So that's kind of one loop of this kind of smart laser-driven source. But then you're able to also interface that with all of the high energy density codes that we have to actually be able to direct the laser to pick a new laser parameter scheme to optimize, for example, your proton energy of your laser-driven protons. So this is kind of where we're going. As part of my PhD research, I worked on this kind of data analysis piece and being able to analyze and collect data at rep rates. I'm not going to go into that because I think I'm perhaps running out of time. But I am going to talk a little bit about this other piece of tunable sources. So this is kind of the subject of my postdoc research that's based on all of my experience in grad school and through all of these different residencies and practicums. And what this is kind of being able to develop a more general model for target normal sheath acceleration. So what that means is that I'm conducting experiments to actually radiograph and measure the accelerating field that I kind of showed simulations of a few slides ago. And how I'm doing that is actually using a second TNSA-generated proton source to actually radiograph this electric field. So this is kind of cartoons of those temporally resolved radiographs of our sheath field. Using this data and simulation, we're using kind of machine learning to compress all of that information and to be able to come up with a generalized model that relates characteristics of your sheath field, so the strength and the profile and the temporal dynamics of it, to the characteristics of our protons, in particular the maximum proton energy. So that's what is keeping me busy these days. I'm sorry that I wasn't able to kind of go into more detail, but please talk to me if you have any questions or suggestions or just want to chat about it. And with that, I'm kind of coming to this conclusion that these kind of 3 building blocks have been forming over both these 2.5 residencies in postdoc. And they kind of represent this kind of foundational step towards tunable laser-driven sources. And just to close, I'd really like to thank LRGF and Krell and this entire community that makes this fellowship possible. It's definitely not an understatement to say that it's been a kind of transformative for me professionally, but also personally, being able to meet everyone. All of you are friends and colleagues. And I hope that I can be a resource to folks as they're going through the program as well. I didn't put my email, but I think I'm the only Raspberry at Livermore, like maybe. So if you're at Livermore, please say hi. And if you have any questions or about anything or need advice about anything, I'll do my best to be that resource or find someone that is better at it. So thank you.